Good evening and welcome everyone on this Antwerp Young Minds panel discussion about quantum mechanics. So the Antwerp Young Minds is a group of young researchers who organize all sorts of activities to promote physics, not only among professional researchers, but also the more general public, students and whoever is interested in physics. And this year marks the official year of quantum science and quantum technology. And so all the activities we organize this year are within this same theme of quantum mechanics. And today you are lucky to be present here because this is our main activity of the year within this theme. So what we want to do now is organize a sort of discussion that puts aside the mathematics of quantum mechanics as much as possible, and we dive in to the physical presentation and representation and interpretation of what quantum mechanics actually means physically. And for this we invited 6 esteemed experts on quantum mechanics. Thank you for being here already and taking the time to share some interesting insights with us. Now, for the evening, I will already announce that there's a break planned at 7:30. So if you want to go to the toilet, then keep it till then. And then afterwards, we continue with the discussion. And afterwards, there's a reception where you can ask some more questions to the speakers for now. There will not be any questions taken during the presentations, but you can send them in after the discussions have started via something that will be shown on the screen. And then our moderators, they will try to integrate your questions into the discussion. So, okay, I think we're almost ready to start. But then I need to announce as well the 2 moderators of this evening, Iago and Lucas, who will moderate the discussion, keep everything tidy and hopefully within the time schedule. Please give them a round of applause.
Okay, thanks for the nice introduction, Thomas. So I'm Lucas, this is Iago. So I will also introduce briefly the speakers, because they will introduce themselves, but I will say their names so that they also can get an applause, not only us. So we have, now I should adapt the order, right? Okay, so first we have Pieter Thyssen, from the University of Liège. Then we have Bart Struyven, who recently joined our University of Antwerp. Next we have Dirk Van Dyck, also from the University of Antwerp. Then the one that had to travel the farthest is Franck Laloë, who came all the way from the Castel Brosser laboratory in Paris. Then next we have Jacques Tempere, also from the University of Antwerp. And then last, but certainly not least, we have Hans de Raedt from the University of Groningen. So, yeah, applause, a lot of applause. Okay, great. And so let's dive in with the presentations. We will have 5-minute presentations. Jacques, you can start. And we have a semi-professional timekeeper in the second row, so who will limit the talks to 5 minutes. So please pay attention. Okay.
All right, thanks. So I'm Jacques Tempere here from the physics department. I learned quantum mechanics, or I was taught quantum mechanics in part by Professor Van Dyck, and I learned also a lot of quantum mechanics from Professor Franck Laloë's book that he wrote together with Claude Cohen-Tanucci. So I'm very happy to be a humble member of this. Oh, test. All right, that's better. Not used to this microphone. Usually I teach for smaller aulas. Good, so let's see what I want to say. Let's try to click this. Oh yeah, okay. So let me start by very quickly reminding you, probably many of you know already, about the quantum randomness, which will obviously be a topic here. And I'll do this using an experiment where we send in photons one by one, and nowadays we can do that. We can generate quanta of light, individual ones, and send them to a filter. Filter has polarization of 45 degrees with respect to those of the individual photons that come in. And then, well, let's see what happens. What are the observations that we have? First observation that we find is that each photon will either be completely going through or completely be stopped. So there's not a half a photon, right? That's the quantum in quantum mechanics. That's the quantization. Then the other observation is that, well, it seems we cannot predict whether a photon, a particular photon, will go through or not. So still, 100 years after we set up quantum mechanics, we're celebrating 100 years of the Schrödinger equation. Still now, none of us, none of these panel members, non-quantum mechanics, can predict whether one of these photons will go through or not. What we can calculate is, well, we can calculate the probability distribution, and in this case, it's 50-50 whether these photons will go through or not. So that's, let's say, the state of things. This randomness is being used, so nowadays they can do this little experiment on a computer chip which is only a couple of millimeters in size, and is being integrated in all sorts of devices to that need real randomness, because this randomness is also, as far as we can test it mathematically, real randomness and not pseudo random numbers. Good, so that has some implications. Many of them, too many for a couple of minutes, but one that I would like to focus on for now is determinism, because this was something maybe rather shocking when quantum mechanics came about. So the idea there, to put it very bluntly, is the state of the universe now fixes the state of the universe later. It's very colloquially put, and many hundreds of years people have already spent trying to make this more precise. What do we mean by the state of the universe? What do we mean by the past? These are all things that can be discussed. For example, the past, now with special relativity, we know that, well, the past we have to look also here maybe at the local past, at things near us, from which light could have reached us. So that's one thing. Anyway, but what do we mean by determinism? For a long time, so before quantum mechanics, many physicists were adhering to a very strong or algorithmic version where the idea was, well, you have the laws of physics and they simply fix everything. If you give some initial conditions to them, everything is predetermined. If you think it's final conditions, then there is fatalism. However, as I explained just in a minute ago, this seems to be no longer the case when quantum mechanics comes about. We have this incapability to explain things. So now many physicists go to the second thing. So they say, well, there is actual still determinism. Things still evolve, but we can't compute it. Maybe we don't have to restrict ourselves simply to the wave function of that photon. We should take into account the apparatus. We should take into account the environment in which the apparatus is, maybe the entire universe, and maybe then it might be possible. It's related also to some problems in mathematics that say, well, if you think that you have an algorithm, a deterministic algorithm going line by line, well, there are algorithms, there are stuff that we cannot predict about these algorithms even though they are determinism. For example, there's no algorithm that will tell you whether any other algorithm will halt. And I see I have to stop already, so I'm going to say, well, we can also simply choose that indeterminism is true and accept that there is really something random about the laws of physics. So I think with 0 minutes, I should not try to explain Bell's theorem, which in my view is somehow supporting the fact that things don't have a fixed future traveling along with them. There's no fixed instruction set going along with them.
I think that's the essence.
That's the essence.
To give away to the
Some
audience.
references. Right?
I will.
5 minutes is too short, but yes.
Yes, it's a hard exercise to. So our second guest to give a presentation is Professor Hans de Raedt.
My name is Hans de Raedt. I'm Professor Emeritus of the University of Groningen, Computational Physics. I started my career here in Antwerp in 1976, and at the moment I'm affiliated with the Jülich Supercomputer Center, which hosts the exascale computer, first exascale computer in Europe, and also some of the new quantum computers. I've been working on quantum Monte Carlo methods in computational electrodynamics, simulation of quantum systems in quantum computers, usually also always using the largest supercomputers that were available at the time. And about 20 years ago, I started to use notebooks to address some fundamental issues in quantum physics by developing an event-based method to simulate all kinds of quantum physics experiments. It is through this work I also got interested in the relation between observation, theory, and interpretations. Oh. Yeah, wrong direction, yes. Oh. Okay. So here is my viewpoint. We all know that the theories of physics explain a lot of things very well, and they are very useful in describing a lot of, say, movement and interactions of particles, material behavior, and so on. No doubt about that. And we all formulate these theories using mathematics, but the mathematical beauty and consistencies of these theories does not necessarily dictate how nature operates. Abstract reasoning does not always correspond to our experience. A nice example is the Banach-Tarski paradox, which is an exact result in mathematics that shows that you can decompose a sphere into two other spheres of equal size. This is, of course, totally against our experience, but shows that we have to be very careful using mathematics. Real numbers are also abstract constructs. No experiment has ever measured the square root of 2, let alone a wave function or a probability. So, as we are not sure or we don't know whether mathematics rules the universe, it is perhaps more appropriate to analyze data without relying on the premise that it does. So instead of assuming that physics theories actually produce data, it is sufficient to confront the results of physics theories with discrete rational numbers, that is what we measure in an experiment, and be happy when there is satisfactory agreement. So here is a graphical representation of what I said a few seconds ago. Is there a pointer here?
It's the red button.
Red button? Here, okay, sorry. At the top here we have natural phenomena, laboratory experiments. They produce discrete data, always in the form of rational numbers. And at the bottom, we have a whole bunch of theories, say Newton mechanics, quantum theory, probabilistic models, and so on. And how do we compare? Well, here we take the data, we analyze them by, say, calculating averages, correlations, whatever. In our theoretical models, we do the same, and then we compare here, and if we find a good agreement, we are happy. But more we cannot really do. We cannot jump from here to here. I mean, we cannot claim that this is what is happening here on this level has something to do with this natural phenomenon. That is a step too far. And another thing I want to point out here is that there are experiments, and the previous speaker already alluded to that, which produce data in an event-by-event manner. And in that case, we need an extra device, which is indicated here by the red block, to produce out of these theoretical models the events that we actually observe in the experiment. Oh, Okay. So in principle, interpretations of mathematical symbols of a model do not really help to bridge the gap with observed natural phenomena. I mean, that's my main conclusion that I want to make here. Thank you.
Then it's time for our next speaker, which is a bit closer to home. It's the Professor Dirk Van Dyck.
Okay. Well, I was one of the founders of the electromicroscopy group. I did the theory. EMAT has 60 people. It's the biggest and also the most productive group of electromicroscopy in the world. We have also 11 ERC grants. Now, as theorist, it means that I had to know everything about the working principle. It's pure quantum physics. And I like to compare it to Plato's cave. Remember the allegory of Plato that prisoners are imprisoned in a cave. There's a fire on the outside, and then they only see the projection on the back side of the cave. The reality they don't see. Okay, and Plato says we don't know the reality there. Well, electron microscope is exactly the same. It starts with an electron beam. It's a pure wave mechanical machine. You can only explain the working with waves. Once you think of particles, that's when you detect. So inside, these are waves, up till you detect by any camera. And this is a structure, barium sodium dioxide. The exit wave, after passing through, has amplitude and phase, or real and imaginary parts. So quantum mechanics is in complex space, it's wave space. And then once you record it, then you have an image, and you can even do a two-beam experiment, so let's say double slit experiment with electrons. These experiments are done in Bologna by Merli's group, a good friend of mine who passed away a few years ago, fortunately. In this case, they used a camera that was sensitive for every incident electron. And then you see, after some time, that the fringes are really probability distributions. That's Bohm's concept, okay? So that's what you can calculate are images, but basically images are statistical patterns of where the electrons come. And only there you can see it's an electron, it's not an electron. Before you arrive there, you have still waves. So basically the electron microscope is like a Plato cage. The outside world is the quantum mechanical world. And even the word quantum is not good. It's, of course, Planck has introduced it, but the quantization is a consequence of the fact that these are waves locked in, but basically these are wave mechanics. And then these are by physics world, it was considered as the most beautiful experiment in physics. So what we do in Antwerp, let's say my main work with many things, that because in this field, electron microscopy has been used by biologists, by material scientists, but these are not always the people that go into the quantum mechanics. So this was a very rich field to go into. And there, what my contribution was that if you change the focus of a microscope, you can record different images. And I made a kind of holographic method to recalculate back complex space. So basically, we invert the system from inside the cave, which is our real world, to the quantum mechanical world, which is a complex world of waves. Okay? In this way, we could reconstruct amplitude and phase of the wave function on the detector and calculate back to the object. Okay, so then the points we are working on now is what is happening if you have the collapse. If you have one single electron, it hits the detector, you see it there. What happens then? You see it there, but what happens more? Why doesn't it go further? And in principle, what I did in my work is I made one Hamiltonian system to describe everything, and I could calculate every possible image. And thus far, it always works. So in a sense, up to what Hans said, within the experimental errors, within the statistics, we can predict, let's say, even without any approximations that are worse than that. So in a way, we say, okay, we understand quantum mechanics in the sense that we can calculate images, we can predict every experiment, but if you ask me to explain it to, let's say, ordinary people, I cannot, because in quantum mechanics, we have the I, square root minus 1. These are things that don't exist in real life. Also, the logic that a particle can go to two slits is not our logic. Even the logic of time, is there a beginning of time? These are concepts that we, let's say, may be different from our daily life. Of course, the only thing we have in evolution were our senses. Okay, okay, then I can stop here.
Thank you, Dirk. So for our fourth speaker, it's again close to home, but he came from far. I'm not really, in terms of universities, it's Struyven.
Okay, thank you. So yeah, I'm Struyven, and I'm both in physics and philosophy. So I have one leg in both, so I'm doing foundations of quantum mechanics in particular. Okay. So what is quantum mechanics about? Okay. So when you read books on quantum physics, you will read a variety of answers. Might be about particles, like electrons, quarks. Might be about waves. Okay. Might depend on which kind of measurement you make. Okay. So usually quantum mechanics is presented in such a way that it's not clear what exactly it is about. Okay. But what's for sure is that waves play a central role. Okay. So waves, they're represented by this Greek letter psi in the mathematical representation. Okay, so quantum systems are described by a wave. This wave, how does it evolve? Well, there's a nice equation for that, Schrödinger's equation. Okay. Using Schrödinger's equation, we can make excellent predictions with quantum mechanics. Okay. But what we have to do, we have to not only use Schrödinger's equation, that's one type of evolution for the wave function. This evolution can be interrupted by so-called collapses of the wave function. Okay? So quantum mechanics says, my system is described by a wave, it evolves according to this equation, Schrödinger's equation, but every now and then it's interrupted this evolution by a collapse of the wave function. This collapse, what is it? It's a sudden reduction of the wave function to some other state. The question is, when exactly does this collapse take over from the Schrödinger evolution? The answer you find in books is, well, that's when you do a measurement. So when a measurement happens, then collapse takes over from Schrödinger evolution. But the question is, what exactly is a measurement now? Okay? Because the dynamics of this wave is really going to depend what exactly a measurement is. It collapses upon measurement. If it's not clear what a measurement is, you're having an ambiguity in your theory. Now, what exactly is a measurement? Well, there's no precise answer there. Does it involve some macroscopic apparatus? Does it maybe involve humans? Maybe humans with a PhD in physics? This is not clear. If this is not clear, you're having a problem with the theory. Okay? So this is actually the measurement problem of quantum mechanics. This being said, this theory is excellent for practical purposes. Okay? This, the level of precision of this theory is unprecedented. Okay? But still, if you want to regard it as a fundamental theory of nature, you have to deal with this problem. And here it's illustrated in the double slit experiment. So you send in electrons one by one, and they land on the screen one by one, forming this pattern. And so you get the interference pattern here if you collect all these data. So this is clearly indicating a wave. But each single electron is represented by a wave. So at the screen, it's really smeared out. So how do you account for this localized dot? Well, there's collapse of the wave function. Now, there's alternative theories. Okay? So this is one of these alternative theories which I've been working on, and that's called the Broglie-Bohm theory, after its inventors, or Bohmian mechanics. This theory says, well, the world is made out of point particles. Tables, chairs, it's all made out of point particles. How do they move? According to a certain law. This expresses that the velocity is given by some function that depends on the wave. So the wave is still there, okay? It's Schrödinger's equation. There's no longer the collapse postulate. For example, in a double slit experiment, trajectories will go through one slit and will produce one dot on the final screen. The interesting thing is, so there's no collapse, no intrinsic randomness, so this theory is completely deterministic, yet it reproduces the usual predictions of quantum mechanics. Insofar, these are unambiguous. Okay? I had a further slide, but I see my time is up. I'll just leave it here to read.
Thank you, Raedt. And then for our next speaker, we go to Franck Laloë.
Okay, thank you. Okay, I'm Franck Laloë. I come from Paris, and I did most of my career on experiments on optical pumping, nuclear polarization, and quantum gases, and spin waves, all these things. So I'm supposed to summarize all of quantum mechanics in 5 minutes. So this is kind of a challenge. So do I press this button to have my slides? No, this one? No? I'm going backwards. Okay, so I think it's unfair to speak of quantum mechanics without saying a few words about how wonderful this theory is. So you all know that, but we all like to discuss about foundation, but it's really a fantastic theory. And it's, for instance, it explains why we are here. It explains stability of matter, which cannot understand within classical mechanics. It explains chemistry property of molecules, solid-state physics, transistors, computers, lasers, and so on. So it is a fantastic theory, but it has, the problem is that it has strange internal limitations. And basically, it arises because, as Raedt just explained, it uses a unitary dynamics to predict the probabilities of an ensemble of identical experiment, but it said nothing about what happens in a single realization of an experiment. So after all, we could say, oh, that's fine, and the theory is fundamentally undeterministic. But still, okay. So here's an experiment which, in my mind, summarizes the main internal problem of quantum mechanics. I assume that I have a single atom coming in this way. This is a beam splitter that we can do with lasers. And then the particle propagates along 2 paths. So when it propagates along these 2 paths, the states vector system is this superposition. Now, a little later, the atom reaches detectors. So if the atom goes in the upper branch, it excites the detector D1, D2 remains silent, and the converse is true. And if you go further, if you assume that you have electronic systems that amplify the signal and register the results, then these registering systems reach different states, and so on. At the end, if you assume that you have 2 observers, Alice and Bob traditionally, at the end of the experiment, they reach a superposition where O1 says, I have seen a result in this branch and none in the other branch, and the converse is true. So this is the well-known fundamental grass, which never ends. One gets the feeling that, thank you, that this superposition will last forever. This is what Tony Leggett calls this QS-MDS, quantum superposition of macroscopically distant states. So, no, I keep going backwards. So, there are, of course, many interpretations which try to answer this question. The most famous interpretation is, as you know, the Copenhagen interpretation, which is complex, and I don't have the time to discuss it since I just have 1 minute. There is the Vonderman interpretation, which Vonderman proposed a projection postulates that the word mentioned just before. There is the DBB, what I call DBB, de Broglie-Bohm approach, which adds variables to the formalism of quantum mechanics. There is the Everett interpretation, which is the branch universe, which is very popular among quantum cosmologists because it's very convenient for them to do their theory. There is a whole class of theories which change the Schrödinger dynamics, modify it to include the fundamental postulate in it, GRW, Gerhardt-Riemann-Weber, spontaneous collapse of impulse and so on. And for instance, there is the Sir Penrose's suggestion to relate quantum collapse. And the problem, it's finished. Okay, so the problem is that we have all this interpretation, but actually no one really knows which is the best, and this is the sad about the situation. Thank you.
Thank you, Frank. Then we go to our last presentation of this introductory section. And so the last speaker is Pieter Thyssen.
Yes, thank you. Good evening, everyone. I certainly feel like the imposter on this panel. I wasn't trained as a physicist, I was trained as a chemist. Now, don't shoot me yet because it becomes worse. After my training in chemistry, I trained in philosophy, and I'm now working as a philosopher of science in Liège. Having said that, I would like to build on what was just said by these fine gentlemen. And so I wanted to first point out that we're dealing with a really unique situation, I think, here in physics when you compare it to all the other physical theories. Namely, mathematically, the mathematical recipe of quantum mechanics, I mean, is fine enough. It works perfectly. Scientifically, quantum mechanics is probably the most successful scientific theory that has ever been developed, and we just saw a few of the important applications of quantum mechanics. But philosophically, I would say, quantum mechanics is a real mess. And as both Raedt and Franck already alluded to, the origin of this mess, to a large extent, is this infamous measurement problem and trying to understand the real nature of measurement. And so in order to try to resolve this problem, which is something that Bohr and his collaborators and Einstein and Schrödinger already tried to do, but which we have continued trying to do, different interpretations of quantum mechanics have been developed, and you see here this whole list of interpretations. There are far more interpretations than just the ones you see here on the screen. There are tens of different interpretations of quantum mechanics. We don't have that with any other physical theory. We only have this with quantum mechanics. And the problem is that all of these different interpretations are mutually incompatible because they tell very different stories about the world in which we live, about the nature of reality. That is, they posit, to say it with philosophical jargon, a different ontology. So for example, according to some interpretations, like the Copenhagen standard orthodox interpretation, quantum mechanics is fundamentally indeterministic. Yeah? Jacques already alluded to this. But other interpretations, like Bohmian interpretations or the Everettian interpretation, are fully deterministic. Some interpretations only posit waves. All we need are waves. Bohmian mechanics feels the need to postulate particles as well, so there we have a dual ontology. Most of the interpretations are very happy with just one unique universe. Everett is going to postulate an infinity of universes. So clearly we have very, very different stories about the nature of reality. And the question is, how can we determine which of those interpretations is the correct one? The trouble, of course, is that they are all empirically equivalent. And so they make the exactly same predictions that you can go and test in the lab. So it looks like it's going to be very hard empirically to go and verify or falsify one or the other interpretation. Finally, to end, I wanted to make maybe a more philosophical point, which is that I would refrain from talking about interpretations of quantum mechanics. I think actually it would be better to talk about different theories. After all, if we take Bohmian mechanics, for example, we still have the Schrödinger equation, but we added a new equation, a new law of motion, which governs the evolution of the different particles. If you go to Gerard Rimini Weber's interpretation, they actually modify the Schrödinger equation by adding some kind of stochastic term that is responsible for the collapse of the wave function. So we have a whole bunch of different theories and no way of really empirically determining which of those theories may represent the correct theory. I'll leave it at this. Thank you.
Thank you, Pieter. So with the introductions behind us, it is time to start the actual discussion. And so for our, let's say, our first subject is just, we're keeping it more still general. So what is the minimum amount of questions, of what are the basic questions that an interpretation of quantum mechanics should answer? So we have heard about the measurement problem. There is a question about the nature of the wave function itself. What does it represent physically or even mathematically? Maybe that's more clear. But so what are the basic, let's say, maybe it's not a correct word, but what are the basic properties that a good interpretation should have to give us a satisfying answer to these questions? So if you want to speak, just press in the microphone.
So here I would agree with Pieter, and it's really about like different theories, right? And like with any physical theory, what's important to be clear about is what this theory is about. So what stuff is made out of, according to your physical theory, and how it moves. Okay, so you have to be clear about what Pieter called an ontology, what exists in the world, particles, waves, strings, something else, doesn't matter. You have to be clear about that, and then also have a clear dynamics. Okay, being clear of how the ontology evolves in time. Okay, so these are two important criteria for a clear physical theory. And then, of course, it has to be empirically adequate. It has to make the right predictions. Okay, so at least these three things, I think, are essential for a good physical theory.
Anyone else wants to add maybe something, some important ingredients?
Well, we also have to think of what we really want to achieve. I give an example. Suppose that nature that represents itself in numbers. That's Plato already said that. And the only thing we can observe are objects at positions. You can argue on that, but I think that's true. Everything others is indirectly derived from that. Even speed needs time. Time is not an objective measurement. Einstein said, when the train arrives in the station, it's 3 o'clock. It means that at the same moment I see the train arriving, the pointer of the watch is at 3. These are two different motions. And if you compare them, you try to find the simplest relationship. So everything we try, already from evolution, we try to understand, to predict, to survive, and we try to understand, let's say, patterns, relations. Of course, before Kepler, you had also Ptolemaios. People could also predict the positions. Kepler came, he made a much compacter. Of course, he was paid to make, let's say, predictions. Okay. But then Newton came and he made it even simpler. So suppose we could make a worldwide competition, universal competition. between, let's say, the best way of describing mechanics. Of course, you have the equations of Newton. He invented, mathematics. And he made, at that time, the most compact expression of all these measurements. And for the time being, it was very accurate. Okay. In my view, in the competition, if you do the same competition universally wide, and there would be intelligence, maybe they come up with the same structure, because then the mathematics is already included in the data. I'm not saying why, that's maybe philosophy, but the mathematics is there, we have to discover them. Of course, there is also mathematics that has been invented also, and afterwards discovered, like Hilbert spaces. But string theory is still an invention and not a discovery. So in a sense, mathematics is a playfield for mathematicians, which is very important. And sometimes it happens that it makes the description most compact. And then I think the most compact expression is the best, like Occam, okay? So why should it be the most compact? Okay, I don't know. It can be more symmetric, it can be. But why, I don't know. Maybe that's in nature. I don't even know why it's in nature. But I think it's observation of mechanics. Quantum mechanics is derived, let's say, we have a theory that can predict the outcome of every experiment. What is happening inside? Well, David Mermin said, shut up and calculate, all right? If you had, let's say, the formulas to calculate, and it matches with the experiments, that's all there is, okay?
Okay, thank you. So, shut up and calculate, I propose that we talk a bit longer, right? So, also we've... Jacques, you want to add something?
Yes, so maybe rather than give a big list of all these possible interpretations, it could be useful for yourself to classify what you believe in. For example, do you believe that the wave function is something real, or do you believe it's merely some mathematical tool that will help us to compute things? And then, if you believe that the wave function is something real, do you believe that it describes all of reality or just part of reality? And then a question like, well, we have update rules for this wave function. Do you believe it's all the time deterministic, or do you allow for some indeterministic steps? So I think rather than giving a list of many names, maybe you could see that with every question you double the amount of possible interpretations. So I think it's useful to think about some of these questions to classify these theories.
Okay, thank you. I'm just going to use this. So we handed out a few papers in red and blue for each of the speakers. So I propose that we test it with one of the questions that Jacques proposed. Like, is the wave function a real physical entity, or is it just a mathematical tool? So blue is agree it's a real physical entity. Red is it's a mathematical tool. So you can vote. Frank? Oh, okay. Okay, so we had, keep them up a little bit longer. We have three, everyone blue, one red. One red, okay. So let's start with the red one, right? Because this is the most controversial opinion. So the wave function as a mere mathematical tool.
No, well, it's a mathematical object. And if you want to speak about or going beyond the mathematical object, you have to go to the question, what is the reality of the square root of 2? So as long as you stay in mathematics, all is fine. But if you start to think this psi, whatever it is, a mathematical object has some contact to reality, this contact to reality is only through the correspondence, say, with calculation in comparison with experiment and successful agreement. Nothing else. That's my point of view.
Somebody wants to give another opinion, maybe? Okay, Dirk.
Yeah, in my view, it's not pure mathematical tool. Take Newton's equation, that's a mathematical tool, but it predicts all the experiments. So in a sense, it's the best mathematical tool to predict the experiments. So in a sense, without experiments, you would not have had Newton and not his equations. So I'm inclined to, it's not pure blue, but it's inclined to be a mixture of two. Beauty can also be important, but we can comment on that, on symmetry and beauty.
So maybe let me pull this back then to classical mechanics, where we describe the world through positions and velocities. Do we believe that these are real? That these are really represent, they're mathematical objects, but somehow we think that the position of an object is something real and that its velocity is something real, something actual, that it describes reality, that it is our reality.
Well, I agree that it is a good representation of what we observe with our eyes and so on. And in that sense, it's a very useful way of describing things. But they're still real numbers. In that sense, they are mathematical concepts. They only live in our brain. We never measure a real number, never. We never measure a momentum. We only measure approximations to it. And if they agree very well, it's fine.
Okay, so yeah, Pieter.
Yeah, I just wanted to add to the question that was asked is there is a distinction that they make with all these interpretations between what they call a psi-epistemic or a psi-ontic interpretation. And so most of the interpretations are psi-ontic, so they take the wave function to be real. The question, of course, remains, well, what exactly is the nature of this wave function? This is maybe something we can talk about later. But I just had a brief look at the list here, and I think it's especially the informational interpretations like cubism and others that are the psi-epistemic interpretations. And so they take the wave function not to be something that is really out there, that is part of the world in which we live, but to actually just represent our knowledge, our lack of knowledge about a quantum system, or they treat it as a computational tool. But I would say that most of the interpretations in quantum mechanics are realist interpretations that take the wave function to be real.
Okay, thank you for this clarification. So as a next question, because we're looking at the list now, on top of the list is the Copenhagen interpretation. I think it's usually the case if you have lists of interpretations. So maybe we can take another vote, because the Copenhagen interpretation sometimes is seen as problematic, but maybe you can vote, is it problematic or is it sufficient? So if you think that Copenhagen interpretation is not problematic and sufficient to describe reality, then you can do blue and otherwise red. Okay. Problematic is red, and not problematic is blue. Oh, okay. So okay. So maybe let's start with people that are not ambiguous about this. So, for example, Dirk, why is it not problematic?
Well, I showed you this result of the Merli group, the two-slit experiment. Then, that theory, you predict intensities. Then you shot one electron at a time until you have 1 million or millions, and it perfectly fits the theoretical predictions. So it means what we calculate is intensities. That's what we calculate. It's the square of the wave function. And then we see them electron by electron, and there's a nice thing with electrons because they are fast and you can detect them as a single spot, you can count them, and then you see really, and you can count, and within the statistical errors, they fit more perfectly with the, let's say, with the statistical interpretation. So I have no problems. The only problem is, why is the Copenhagen interpretation there? I cannot prove it. I see it works, and our theories predict intensities, and we say this is Copenhagen, excuse me. But why is it? We don't know yet.
Okay, I have to pick. Okay, so what was the question again? Because it's important how you
interpretation problematic.
Yeah. Well, so on the one hand, it's a very good theory, right? And as Dirk said, surely it makes excellent predictions. So in that sense, it's extremely good. But you also, or quantum mechanics at least, has the aim to be a fundamental theory of nature. Okay? Not only being good at making predictions for experiments, but also describing how the world is. Okay? And then you have this measurement problem. Okay? You have to invoke the collapse of the wave function. If you want to have definite outcomes in experiments, then that wave function has to collapse. Okay? And then you have this problem, when exactly does it occur and all that. If you don't make that precise, you have an ambiguity in your theory. Okay? But for practical purposes, it's excellent. Okay? But if you want to regard it as fundamental theory of nature, you have to do some more work. How that should be done?
A word about the collapse. You know, as I said, we try to put everything in an Hamiltonian, the electron, the object, the sample, the detector. But even an electron or a photon that hits a screen, it's an atom at the screen, it excites an atom, and the atom emits again light. So you can include the atom also in your set. And then you say, okay, but these lights go to the other thing. It goes to our brain, to the retina. You can include the retina. So this is, let's say, not limited. So you can include everything up to the human brain. And then Penrose said it happens, the consciousness happens at the collapse. Perfectly, I think it's never collapsing. But I have some theory about it, and it's maybe too early to discuss about it. But it never collapses. The only thing is we cannot discriminate it because our senses are not sensitive enough to see these waves.
So, but if the wave function doesn't collapse, it's already not standard quantum mechanics. It's already a different theory.
You're right, you're right.
I think Jacques wants to say something. You can push up the button above. Push it up.
Test. Okay. So I'm a fan of the Copenhagen interpretation, and I don't mind the collapse, but I do have to admit that if you ask me to give a precise definition of a measurement, I'm in trouble. I mean, I know one when I see one, but that's not good enough of a thing for me. So yes, that still bothers me. But apart from that, I'm perfectly fine with that there would be a rule that says, okay, this and this and this is a measurement. If this occurs, then there's a collapse. No problem for me.
Yes, so we will actually discuss the measurements problem a bit later. Frank, maybe we can also hear your opinion, because you also had a red card, right? Yes.
Can you take the microphone?
Jacques?
Strictly speaking, the collapse is not part of the Copenhagen interpretation. The collapse was introduced by von Neumann later when he wrote his book. Bohr never spoke of collapse. He spoke about the cut between the word of objects that we can describe in common language and the word of macroscopic objects that cannot be described by the same language. And to him, the wave function was probably the tool to connect these two worlds. So it was not really itself, it was something to connect to different, very different concepts. Now, one more word about the different subjects. In our discussion, we oppose deterministic theories and non-deterministic theories. I would like to emphasize that, according to me, none of these theories is deterministic. For instance, if I take the Broglie-Bohm interpretation, it replaces the random process that occurs during the measurement by a random process that occurred before at the creation of the world, and which decide where the Bohmian positions are. But we always need some random process somewhere. It just moves the time at which it occurs.
Thank you, Frank. I think that was a very interesting point. To maybe pivot the discussion in towards the next topic. So we have these different interpretations, or let's say theories. And let's say the Copenhagen interpretation just gives us the probabilities of observing some measurement, let's say. But is there any way of distinguishing these different interpretations? Do they, in their theories, introduce some things that could be maybe used or even abused in experiments to maybe find some incompatibilities between these theories?
Yeah. Maybe we can take a vote if there is, in principle, if there exists an experiment that can distinguish between interpretations, right? So blue is if you believe this experiment exists in principle. Red if you say it cannot exist.
They exist now, or they are possible?
Principle. If they are possible in principle.
That's good. Do you mean now or in the future?
Okay, we can say in the future, and then we can, after that, okay, we have one red vote. Let's also do the vote in 10 years. So we had in principle, and now we have in 10 years. There's still some optimism, I see. So, okay, again, it seems I had expected it to be more split, but we have again one contrarian vote. So Hans, tell us why, even in principle, such an experiment cannot exist.
Hello? Okay. Since all these, say, variants of interpretations predict the same experimental results, no way to distinguish.
Okay.
That's it.
Short and simple answer.
Yeah,
so now...
so one interpretation here is missing, and that is a statistical interpretation. The statistical interpretation has none of these problems, absolutely none of them. But of course, it doesn't say anything about single events. So, okay, that is what we have to live with. We know that there are experiments, like Dirk was saying, with this, say, the Tonomura experiment with single electrons that produce single events. And this question of, say, describing these single events, that is out of quantum mechanics. If you want to force it in, or rather force it out, you end up with this list. And if you don't want that, then there is no problem.
You mentioned, so all these theories give the same experimental results. But is that maybe at this moment a consequence of some practical limits on our experiments? Or is there any possibility of pushing our experiments to such a limit that we maybe can discern, let's say, little bugs in the theory?
Sorry. Of course, in the lab, at least most things we measure in the lab are still explainable by quantum mechanics. But if you read the book of Hertog and Hawking, they predict the origin of the Big Bang quantum mechanically. Okay? That's when you also include gravity, everything. And there are experiments being done. You can look at cosmic background radiation. But recently, we will have an Einstein telescope, hopefully in Belgium. And there we can look very close to the Big Bang, and there are still open questions. So I'm quite sure there will become new experiments, not yet today, but certainly in the near future. And this is at the limit of quantum mechanics, because we think Big Bang, Lemaitre, Belgian priest, was one of the inventors of the Big Bang. We think there is a time origin. Why is there a time origin? You don't know. That's our logic of daily life. Our logic of daily life also says an electron can also go to one split. So maybe time itself is quantum mechanically not determined. I mean, not origin as causality. It starts somewhere. Maybe you have to live with that fact. But there will be new experiments that can be very high. That's why I put blue here.
Yeah. Maybe, yeah, Pieter, for example.
Yeah, I had one particular interpretation in mind which I think can be tested or falsified, which is the GRW interpretation, the Gerardi-Rimini-Weber interpretation, because in order to solve the measurement problem, it basically posits that each and every particle has a chance of collapsing and of obtaining a very definite position in space. And so they usually live in a wave state and they're smeared out over space if you want, but from time to time they get collapsed to a very well defined position. Now that chance, the frequency of these spontaneous localizations is a very small frequency because of course you don't want an electron to collapse every second because you want to be able to create superpositions, you want to have interference effects, and so it's important that a superposed state is stable enough and can exist long enough in order to have all these quantum mechanical phenomena. On the other hand, if particles wouldn't collapse frequently enough, then not only could an electron be put in a superposition for a very long time, but bigger and bigger objects. And so you could have a cat, Schrödinger's cat, that could be in a superposition of being dead and alive. That's something we don't want. And so these three Italians, Gerardi, Rimini, and Weber, really fine-tuned it. They actually introduced a new constant of nature, which is the frequency of collapse, that was chosen such that small quantum systems are stable enough, but of course macroscopic objects could never exist in such a superposed state. Now of course there's the microscopic and there's the macroscopic, but there's also the mesoscopic. So there may be a point where we could perhaps in a lab create mesoscopic objects in a superposition, or where we could create a two-slit experiment, but not with electrons or with photons, but with bacteria or small molecules or something big enough, and that could potentially falsify at least, I think, the GRW interpretation.
Okay, thank you. So maybe we want to hear some other speakers before the break. You can quickly speak.
On the two-slit experiment, this has been done with 60 particles, very heavy particles that interfere with themselves.
Okay, that's insufficient to test these models yet. But so these collapse models can be not yet ruled out by these experiments. Yeah. These are impressive experiments, but they can't yet be ruled out. So that's how well they're constructed. But there are like spontaneous collapse models that have been ruled out already. Okay, so people are doing tests as we speak of these models just to test them. Okay, so and within 10 years we will know for sure, I think.
Okay, yeah, but maybe Jacques wanted to say something. Maybe you can say something about testing other models than the spontaneous collapse models. Proposes an experiment for the next 10 years, Jacques.
We've already heard some experiments, so I was going to say that the experiments have been done. In fact, the Bell test was a sort of experiment to rule out local realist theories or to rule out some interpretations, so that has been done. And now people are putting heavier and heavier objects in quantum superposition. There's the group of Marcus Arndt in Vienna who's doing that, trying to, in the end, put living things in superposition, small viruses first and bacteria. Let's see what happens. Also, a nice breakthrough is that people are creating extended wave function, extended object, Bose condensates, in a gravitational potential, and they can measure the gravitational redshift already to a level of accuracy where they see the difference of clocks over a millimeter. That's really amazing, and I'm sure that these kind of experiments will lead to breakthroughs. Also, the advances that are being done now in quantum computers, maybe we will not use that for factorizing prime numbers, or maybe we'll use it once to demonstrate that it can and then never do it again. But I think this holds a great promise to test fundamental ideas of quantum mechanics, and that's something that's just around the corner.
Okay. Maybe Hans can just quickly counter these arguments, and then we will go to the break. So keep it short, Hans.
Yes, I would like to comment on the, double slit experiment, because it has been mentioned several times by now. I also mentioned in my introduction that we developed some time ago a discrete event simulation method to do these things. And I can assure you, you can simulate interference experiments, just as the ones that were shown here, one by one with elephants. It doesn't matter whether they're quantum particles or not. You can do this on a computer. Of course, it's easier than doing it with elephants, but you can do it. And there is no quantum or wave mechanical aspect coming in at all. They're just solid objects, imaginary object, of course, if we do it on the computer, but you can get exactly the same results out as the ones you get with wave mechanics. So the idea that interference is a wave mechanical phenomenon is just plain wrong. Of course, you can now keep going on and trying to interpret this in whatever way. You're just turning around to things, you know. You never get out of it. Like Einstein said, you cannot solve a problem on the level it is created.
Okay, I will interfere with this discussion now. So we can go to the break. We have a 10-minute break, so you can go to the toilet, and we come back here at 7:50. Thank you.
During the break and during the next round, you will have the opportunity to submit questions should they occur. So you can go to that link or scan that code on your phone, and then you can submit your questions, and maybe they'll make it to the speakers. So welcome back, everyone. We're going to continue the discussion. And so for our next topic, it's been come in the focus already a few times, but we're going to talk about measurements. So maybe a first important question really is, what is a quantum measurement, or a measurement in general? What does it do? What should it do? What doesn't it do? Yeah. Does anyone want to start?
Yeah, so maybe I should also clarify, we will try to get the questions into the discussion, right? So we will mention the questions as much as possible in the discussion. But now we start with because our topic is measurement, we start with a very fundamental question: what is a measurement, right? So, yeah, in the context of quantum mechanics, does anyone have an answer on this question?
So you can ignore the questions behind you for now. So our question is, what is a measurement? Just in general, or in a quantum context, what is it? What are the fundamental properties of it? Or yeah.
I can maybe say something about it. So usually if you use the word measurement, the connotation you make is some physical variable has some value. I don't know what it is. I'm going to look and see what it is. I don't know what the color of the paper below is. I just look, it's blue. So I just look what it was. Okay. But with quantum mechanics, it seems to be something different. And that applies, I think, to all these theories, basically. If you're going to do a measurement, most of the time you're not revealing some pre-existing value, okay? So a measurement is really an interaction with a quantum system of a certain nature, okay? So that's a lesson we got from Bohr. A measurement process, you have to include the measurement device and the quantum system as well.
Okay, so it's not only about observable, but also about device, right?
But you have to, if you want to talk about measurements, you have to not only talk about the system, but also operational procedures, what exactly you're doing in your measurement. For example, if you measure spin, you have to be clear, I'm going to perform these operational procedures, like putting in a magnet, okay, to deflect beams and so on.
Okay, but some interpretations also include the measurements not only as a description of the apparatus, but also as a more fundamental thing where something happens to the system, right? But maybe none of you believe that these theories are correct and that it is actually important. I don't know if anybody wants to comment. Okay, this question was unclear. Okay.
For Bohr, there was definitely a difference, right? Like as Frank said, for Bohr there was like a quantum world and also a classical world. And your measurement device that was part of the classical world could be described with classical mechanics, okay? But like, I think, I don't know, part of the problem, like the measurement problem, is to take measurement as something primitive, something fundamental, some very particular physical process, okay? And that's where it becomes problematic because you don't know what exactly is a measurement apparatus. Okay. It becomes, for example, less ambiguous if you say maybe consciousness collapses the wave function. Wigner once proposed that.
That's a good point. I also saw this question appear, so let's take a vote. Does consciousness collapse the wave function? The question is, does consciousness collapse the wave function? Okay, that's clear. So there you have it from all of our experts.
Just a small comment. Wigner was invited here at RUCA, I think 1975, with his theory that the observer should be part of the experiment. Wigner here.
I mean, if I can just say something about Wigner's interpretation. His idea was, when does the wave function ultimately collapse? And his idea was that no physical system can cause the collapse. And so what we need are indeed human beings or maybe some other animals that are conscious. And he took consciousness to be something non-physical. The mind is a non-physical entity. So the idea is that if you open the box of Schrödinger's cat, even your brain gets into a superposition of observing a dead cat and an alive cat. But at that point, your mind, your consciousness, the aphysical mind, looks upon your brain state that is in this superposition, and that is causing the whole superposition to collapse and the world to take up a very definite state. So obviously, in order for this interpretation to work, you need to have some kind of Cartesian dualism where there is a physical world and an aphysical world. And somehow the two of them are interacting with one another because it's the aphysical mind that is causing the collapse in the physical world. Now, if one thing has been kind of, erased from the table in philosophy, it's Cartesian dualism. And so I think Wigner's interpretation never really had any chance of success. But it shows that even someone who won a Nobel Prize in physics, one of the greatest minds of the last century, it shows to what extent how far he wanted to go to actually find a solution to the measurement problem. And I think it's very natural for not only Wigner, but people like Penrose and others to connect the two big mysteries, the mystery of consciousness with the mystery of the quantum world, and to maybe think that there may be some kind of intimate connection and that maybe consciousness really plays a fundamental role in understanding quantum mechanics. But I'm definitely not convinced.
Hans?
There are a lot of maybes there, but maybe this is just a religion that you're introducing, isn't it? You're making it a religion. You believe in certain things and then you want to impose your belief on what you have seen. Okay, that's a religion. And this has very little to do with scientific enterprise, where you analyze data and try to make sense out of it. Order the data, see the relations between data, and so on. I mean, that's another enterprise than just saying, I believe this or that, and I'm going to try to fit what I've seen into my belief. I mean, that's a different enterprise, I would say.
That's a fair point, but maybe I would also like to ask you still about your beliefs, if it's not too personal, because we heard about the collapse of the wave function a bunch of times, but do you actually believe the collapse of the wave function is a physical thing that happens? So maybe you can vote again. So Raedt, if you don't believe that it actually, there is a wave function that collapses. So blue means wave function collapse is a real physical thing, and red means it isn't. Which wave function are we talking about? Your favorite wave function. Okay. Yes, Dirk.
People tend to believe that without consciousness there is no collapse. I take my microscope, I count individual electrons, I put a photoplate there, I go outside, someone put it on, I come back, without me being there or not, it's exactly the same experiment. So these collapses happened without me. Or maybe you include me in the wave function as far as I go, but I'm inclined to think that interaction decreases with distance in some way. So I think the collapse is there physically. How you interpret it is so different. How I try to include it in my own work is I include now the detector in the work, because nowadays our theories are good enough to also include detectors. See what's coming out. And how far does it go? Until my brain, the last part I cannot. So here I still am wiggling between what is then consciousness or not. But I think you can extend this at all measurement within your function, within your quantum mechanical description.
Jacques, you want to add something?
Yes, I completely agree with Dirk. It's the detector, to me, that collapses the wave function. And I can add a personal testimony, because a long time ago, during my postdoc, I was doing experiments, and these were late-night experiments, running all night. And I can confirm that the wave function continued to collapse also when I was unconscious.
So, I'm glad you're conscious now. I want to maybe go a bit further into this this collapse. So, regardless of whether we consider it physical or not, but so consider, for example, the wave function of some particle as it collides with the detector or whatever it does. When does the measurement occur? I asked this question because I saw it once in one of the Ward's presentations. So when you have this wave function of the particle and it comes to the detector, does a measurement or collapse occur the moment the wave function touches the detector, or does a significant portion of the wave function needs to go through the detector, or is it not a sensible question to ask in the first place? Hans, I see you want to say something?
I can try to say something about that. So if we go back in history, in 1923, a certain guy called Duane wrote a paper, and he argued that in order to describe the diffraction of an electron from a crystal, you don't need a picture of a wave attached to the particle at all. This paper has been completely forgotten by the quantum mechanical community, and the only reason it has been forgotten is because at the time they would have accepted this point of view, all the mysteries would have been disappeared. No particle wave duality, no collapse, none of these things are necessary. And the point that Duane essentially makes is the particle is a particle, doesn't need a wave, but of course the crystal is a big thing, and the wave is in the crystal. I mean, I'm making it in a simple way, but essentially that is what he's saying. And in order to make a consistent description of all these things, you have to add another quantization rule. Why do we only have quantization of energy and angular momentum and not of momentum? If you add momentum, everything, all these things are gone. So what are we talking about? I want to mention, this is 1923.
No, yeah.
So it's very old. Huh?
Unfortunately, also electron microscopists are also people very confident with diffraction, because it's a push button, you see the Fourier space. If you have a lens, the back focal plane of a lens is the Fourier transform of the object. Fourier transform, let's say, basically, if you expand, in quantum mechanics, you need a basis. You need something to describe a wave function, which is a linear combination. You use a basis. Usually people use eigenfunctions of some operator. If you have a free operator, these are plane waves. Plane waves mathematically is a mathematical basis in Fourier space. You can even describe a person in plane waves. If you put, let's say, what people do in diffraction of proton diffraction, let's say protein diffraction, they make identical protons in a crystal, they do diffraction by X-rays, and they dissolve the structure. So these are waves that are not really the waves of the particle, but waves that sample the particle. So you don't need a wave in the particle. The particle has to be quantized, let's say quantum mechanically, but you can still, let's say, investigate it by waves. Okay? In my view, waves are just a particular basis to work in, and that's what we need. You know, even Cartesian, if you want to determine a position, you need 3 axes. So basically, you always need a base. Also, quantum mechanically, you need a basis to expand this, and plane waves are a basis, which are basically Fourier components.
So that's a good point. You need a basis, but still there is some kind of wave, which is the wave function, which is expanded in this basis, right? So maybe we can hear some opinions on what is a wave function. What I heard you say, what wave function? So maybe you can say something about this.
So then I was thinking about my path theory, this Bohmian theory. Because there, one can distinguish between different wave functions. According to this theory, there's one wave function of the universe. Okay, one wave function of the universe, but we can also have wave functions of subsystems within the universe. Okay, I won't go into the mathematics, but for example, if you have the double slit experiment, the wave function you find in quantum textbooks, in the Bohmian theory, that would be a wave function of a subsystem. That wave function would actually collapse in measurement-like situations. You analyze the measurement in detail, okay? You work out the dynamics and all that, and then you would see that wave function actually does collapse just like the doctor ordered, okay? So whenever there is macroscopic stuff involved, to put it briefly, collapse will typically happen of this wave function of a subsystem. Wave function of the universe, that will never collapse.
Okay, yeah, Dirk?
Just one more. A wave function is just a mathematical construction. We get used to it, we know the properties, but as an example, if you want to describe quantum mechanics in complex space, you need I is square root minus 1. You never observe it in reality. But if you think about it, negative numbers, do you know negative numbers? Did you ever see something negative in your life? Never. Mathematically, you try to make a group with, you know, four properties to solve problems. How much do I have to give it to multiply in order to? The final result is always real. But in between, you use beautiful mathematics to come up with a simple way to solve it, and at the end, it's real. Even you never saw something negative, so if people ask you, explain me what -1 is, you say, oh, 0 temperature, we don't know. Go to the bank, you don't have deficit there, it's always positive. There's no negative temperature, so in a sense, negative numbers don't exist. These are mathematical constructions to make life simple. Sometimes the simplicity even wins For instance, Dirac tried to combine relativity with quantum mechanics. He came up with an equation. He said, I don't believe in an ugly theory. This equation was ugly. It was second-order differential equation. No, he said, I want first order. He came up with the Dirac equation. He predicted positrons. He predicted spins. So in a sense, symmetry and let's say, and simplicity can be a driving force to proceed your science.
Okay, I will cut you there also because we will discuss relativity later. But so, yeah, negative numbers don't exist. I will think of this fact the next time I'm in an elevator, right? But let's bring this back to measurements. There's one very important constraint on theories or interpretation, which also has to do with measurements, and this is provided by the so-called Bell tests that were already mentioned also by Jacques. So what are these and what do they precisely imply about the nature of our universe?
So I need a couple of hours for that. But so what was this Bell test about? There was one interpretation, well, that was one bother that thinking how to explain it compactly. Yeah, so one way to interpret this quantum mechanics is that the wave function is not enough. There is something else, some hidden variables. And if you would include these hidden variables in the description, then it would work out like classical mechanics again. And this experiment of Bell was designed to disprove that theory. So it works with pairs of particles that have perfect correlations and where you can do measurements of different properties. And then you can count the number of times that you measure property 1 being true and property 2 being false, and measure different combinations, and you can set up an inequality that if there are definite numbers of these particles that are prepared in advance, maybe we cannot calculate them because we don't have any knowledge for the hidden variables, but then still these inequalities would have to hold. Quantum mechanics allows us to prepare the particles in states where we violate these inequalities. And so this has been tested. Is it true? Is Einstein right that all this entanglement and collapse of the wave function non-locally into different points in space, that this is something that is not true because it's actually still already encoded in the hidden variables, versus quantum mechanics that says no, even if you delocalize your wave function, if you entangle a particle here and another particle on Saturn, then if you collapse the particle here, the particle on Saturn will also collapse in a perfectly correlated state, then this will happen, says quantum mechanics. Einstein says no, it has to be local, it cannot happen. Experiments have been done. This is one example where experiments have been devised to test this interpretation of local hidden variables, and it was found that it's not true. Of course, so quantum mechanics is right, Einstein was wrong in that case. These experiments are being refined all the time. There are loopholes that people think of. There was a few years ago the Nobel Prize for Alain Aspect, who did the very first version of this, but there's lots of things. Maybe you can put up the slide for a moment again. So there's lots of things that might go wrong. If you use light particles, there might be problems, because if your detector doesn't detect the particle coming on, then it could be simply because it was lost in the meanwhile. So people have been doing this now with electrons, they've been doing this with atoms, they've been doing this with superconducting qubits. Yeah, so let's skip that and go to the next slide. Yeah, why not? Right. So some recent realizations to mention is with electrons in 2015, and then with atoms, that was done in 2017, and then on a quantum computer with superconducting qubits that were placed very far apart so that these measurements could be done so fast that light didn't have time to travel from one to the other. That was done in 23. So there's other realizations that people have tried to extend this that still would have some possible loopholes. That's with macroscopic objects that people have done this, with Bose-Einstein condensates in 2016. And then using light particles that really have nothing to do with each other to set the random timer in, the random choice. So people chose light particles that came from quasars at opposite sides of the universe. So these certainly were generated out of each other's light core to do that. And all of these say quantum mechanics in the quantum mechanical prediction is right, and the assumption that there would be some local hidden variable is wrong. This doesn't exclude Bohmian quantum mechanics because that uses in a way a global hidden variable that is spread out. The pilot wave is spread out, so that is still not ruled out. But local hidden variables are.
Okay, Hans, you want to comment on this?
Yes, maybe more than a comment. So what my colleague here is saying is partially okay with me, but also misses a lot of other points. Yeah, that's not the only thing. So recently we took data from foreign exchange, for the foreign exchange data, which is just numbers taken from selling and buying dollars and other exchange valuta. And if you do the same, exactly the same analysis as people do with their so-called Bell tests and sophisticated experiments, you get exactly the same type of violations as they find in these experiments. Now, I don't think anybody in the audience here is going to claim that what is happening on the foreign exchange has anything to do with quantum physics. Or is there somebody? So what the point of all these things is the following. Exactly the same thing as I showed in my slide. You mix up two things. The theoretical model, I mean, Bell's theorem stands as a rock. There is no doubt about it. And then the second thing is the way the experiments are done. And these have absolutely nothing to do with how the Bell model is constructed. One thing is, my colleague has the point there, coincidence counts. Most of these experiments use coincidence counts. And what that means is that you only use a selection of the data. You don't look at all the data, but only at a selection of them. And you select them very properly such that you get violations. And then you say, hooray, hurrah, hurrah, you know? So we analyzed a lot of these experimental data. We have them ourselves of experiments that have been done. I mean, the collapse doesn't play any role there. I mean, they're on a hard disk somewhere. If you start to analyze these data, you will find that they disagree with quantum theory. They do not agree with quantum theory, they disagree in a serious manner. And the problem is not quantum theory, but the problem is the experiments are not done very well. I mean,
yes.
So this is really these loopholes, right?
No.
This what you are talking about is this coincidence count that you can play with. So when do you detect, when do you know that this is particles from a pair? Just a second. When you know that it's particles from a pair, when they are detected within a certain time window, these photons. And that's a problem. If you play with these time windows, then you can indeed simply with classical processes violate Bell's inequality. But that's why now people have been doing it without coincidence measurement. These are all this progression of experiments trying to eliminate these kind of loopholes.
Yes, it is of course true that they invent all kinds of other mechanisms. But all these, especially 215, 217, and also 223, they all select data in a certain way. They have another, they don't use coincidences, but they have another selection mechanism. And in statistics, it is well known, I mean, this is very old stuff, it's called the Simpson paradox, that if you have data and you start playing around with the data and group data in a certain way, you can get to any conclusion you like. And that's essentially what they do. They know what they want to have a violation. In some of these papers, it's even mentioned explicitly that they tune their software analysis to get the maximum violation. So what does that mean, you know?
Okay, so let's not go further into the big Bell test conspiracy. No, with all due respect. Bart, you want to comment?
Not really comment, but just say the same thing in different words, so maybe I can put it even more succinct. So what Bell's theorem is really about is, well, testing whether a local description of nature is possible. What do I mean by local? Well, a local theory, in a local theory there will be no influences going faster than the speed of light. So for Einstein, that was no go. For Einstein, the world is local, there cannot be, there should be a local description of nature. Yeah, and so what Bell did was, well, if your theory is local, then it has to satisfy a certain inequality. You can go out and test whether this inequality is satisfied in nature. What do they find? It's violated. What this means is, however clever you are, okay, if you're cleverer than Einstein, you will never come up with a local theory that describes the phenomena. Your theory, if it describes the phenomena correctly, it has to be non-local.
Let's reply from Hans quickly.
And standard quantum mechanics is non-local. Okay, so that's no exception. So standard quantum mechanics, the Broglie-Bohm theory is non-local. If your theory is going to describe nature, it has to be non-local.
Yeah, so within the theory, as I said, Bell's theorem stands as a rock and it's a theorem within the theory. The problem is that if you have data and you don't impose a model on the data, you cannot prove that they have to obey the Bell inequalities. Whatever thing you assume, if you just take data, everybody in the audience can do this for himself, take plus and ones as data and try to prove the Bell inequalities. Simply impossible. So, arithmetically impossible. It's almost, say, primary school algebra, that this is not possible. But this is constantly overlooked by introducing the idea that this, say, model of Bell applies to the real world. Of course, if you believe that, then of course you can come to these conclusions. But, so the conclusion is not there is something strange here, the conclusion is you should throw away Bell's model as a model for the data, and not the other way around. You see what I mean? So instead of saying, I do an experiment, for instance, this foreign exchange data stuff, and I get a violation of these inequalities, it only means the model cannot describe this data. You have to refine the model. That's a normal way of doing science. If the data says that the model is no good, okay, let's try another model. There is nothing wrong then. Nothing strange. No, the physics community has decided that because they believe in this model and they find the violation, there must be something strange with nature. And that is a very, very, I would say, a very big fallacy.
Maybe to briefly go a bit further on that. So does your criticism also hold for the other tests? So I think there's a GAZ test and some other, let's say, entanglement tests.
They're all the same.
They're all the same.
In the sense that they all use post-selection or another form of processing to select data from a full data set and do an analysis on the selected set and get to a conclusion.
Okay, thank you. So let's round up our discussion of measurement here and move to relativity, because Bart was already mentioning locality and also introducing the speed of light, which is not in Schrödinger's equation, of course. So in these interpretations, how important is it to take into account special relativity?
Very important, right? Quantum field theory, it's a theory that combines quantum theory and relativity, special relativity. So the statistics described by that theory is Lorentz invariant. But now, the consequence of these violation of the Bell inequalities is that your theory has to be non-local. There have to be non-local influences going on. Also in quantum mechanics, there's non-locality involved, right? If you have an entangled system, as Jacques said, if you measure on one system, there's going to be instantaneous collapse, and it's going to change something on the other side. That's your non-locality at work. But also, while there's these non-local influences, you cannot signal faster than the speed of light. So you have to distinguish these two. There's non-local influences going on, but you cannot use these influences to build a telephone, to phone some aliens in the Andromeda galaxy. No, that's not going to work. But we have a puzzle now, because on the fundamental level, your theory has to be non-local, must have these influences going faster than the speed of light. And the question is, how do you combine that with special relativity? How do you combine that with Lorentz invariance? And that's an open question, and that's what any formulation of quantum mechanics, any theory of quantum mechanics, really is struggling with. Okay? Standard quantum mechanics, you have these relativistic wave equations, so you would think, oh, of course that's Lorentz invariant, of course that's relativistic, but that's forgetting about the collapse of the wave function. Collapse is instantaneous, it requires a preferred frame of reference. That's what's breaking your Lorentz invariance. In the Bohmian theory, you can formulate Lorentz invariant theories, but it seems a bit artificial. Okay? Also for these spontaneous collapse models, it's very hard to construct something that's Lorentz invariant. Okay? So we're puzzled here. Okay? So the statistics is Lorentz invariant. To find a theory that's on the fundamental level also Lorentz invariant seems extremely hard to do. And none of these theories really succeeds in that.
Okay, thank you. So maybe we can take another vote. So these non-local effects, the collapse and the entanglement, does that need like a special frame of reference in which this is spontaneous or not? So you can vote blue if you think that you need this frame of reference in which it is spontaneous, or red if you think that we don't need it. So I will repeat the question. Do we need a preferred frame of reference in which the collapse of the wave function and the spread of entanglement is spontaneous? Maybe too difficult for a yes and no vote. Okay, does anyone want to comment?
No, it's a difficult question, right? So relativity theory and also general relativity, these are very nice theories, okay? And now we suddenly come to the conclusion, yeah, a theory of nature taking into account quantum mechanics has to be non-local. You would like to preserve all these nice symmetries like Lorentz invariance, but just how to do it, how to, like in a satisfactory way, do it, that's a puzzle. So if it can be done, so much the better. If it can't be done, well, we have to look into that.
So I had this question that popped up earlier to me this day. So I was reading something that you wrote, and you mentioned that this pilot wave goes on in the configuration space, let's say. And when we talk about locality and so on, it's usually restricted to our, let's say, our physical space, or our three spatial dimensions and the one time dimension. But is there maybe some sense into that we need to construct like a more complex space, or including this, let's say, a compound space of the physical space and the configuration space, where maybe when you then go to talk about locality and so on, then suddenly things are local, just because the space is become so warped in this compound space, and then that you have no problem really about locality. It's maybe a bit too advanced question. I don't know.
So I think that's really an important thing, and that's usually not appreciated so much, right? In Newton's theory, you have something like three-dimensional space and one time dimension, and you have particles moving around in that space. With Maxwell's theory, there's additional stuff. There's electromagnetic fields propagating in space. Now with quantum mechanics, if you take the wave function seriously, as part of the furniture of the world, okay, as part of the stuff, as a thing that stuff is made of, well, the wave function doesn't live in three-dimensional physical space. Because if you consider two particles, that wave function is a function of a six-dimensional space. If you consider n particles, that function is a function of three n-dimensional space. So that's not an object that lives in physical space. Okay? If you now want to talk about locality, relativity, okay, it's locality in space. Relativity, Lorentz invariance, it's about symmetries of space-time. Okay? If you don't have stuff in space-time, maybe space-time doesn't even exist according to that theory then, well, this discussion about locality or non-locality doesn't even get off the ground. So this is particularly relevant for this many worlds interpretation. That states that the wave function is the only real thing. It always evolves according to Schrödinger's equation. If you take that seriously, then you have to say, well, space-time does not exist on a fundamental level. Maybe this higher dimensional space exists. Maybe just some Hilbert space exists. And that's the real physical arena. And what we perceive as this three-dimensional space plus one time dimension, that's just emergent. So if you take the wave function as the real thing, space-time is emergent and stuff in space-time is all emergent. Okay? So you have to make an effort to tell how that emergence goes. Okay? But stuff like locality, well, you don't have to worry about locality because you don't have space-time on a fundamental level. Maybe in this abstract space then, everything is local there. That might be so, but that's a different question then.
Okay, maybe, yes, Jacques wants to comment.
So maybe still on this combination with special relativity. So one important aspect is the covariance of space and time. But another difference that's important between, let's say, the quantum field theories and regular Schrödinger mechanics is that if we combine it with relativity, now there's a possibility, if there's enough energy, that particles get created. If you have the Schrödinger equation for one particle, it will always be one particle. We need these quantum field theories to also include processes where you can start with one particle and end up with more than one particle.
Okay, that's a very fair point. So maybe we can talk a little bit more about quantum gravity and space-time and these kind of fun topics. So maybe I'd like to ask you, is there such a thing as a superposition of space-times? Do you want to vote? Maybe we can vote again. Just speculative. Hello? Yeah. Blue would be a superposition of space-times, should be something that exists, and red is it shouldn't exist. Some doubt. Okay. What? It's just a belief. Okay. But maybe Hans, you can again comment.
Why would we need that, you know? So why ask the question at all? Is there any evidence that we need this?
Well, I think that most people like to believe, but maybe you don't, that we in some way have to have a theory that has both gravity in it, right, and space-time, and the quantum aspects. So then, in some way, you can wonder how far does the quantum get into the gravity, right?
Well, I think in my mind, they are not compatible. So quantum mechanics is a probabilistic theory, and the other one is not. And you cannot get the other one out of a probabilistic theory. That's very simple. You cannot get Newton out of probability theory. I mean, you can try, and maybe in 100 years, we come to the agreement that you cannot.
So, now saying that let's say the theory of gravity is not non-probabilistic, but then if we go back to, let's say, the Big Bang, let's say, and then usually what people say is you have these quantum fluctuations, and then during the expansions these become magnified, let's say, in some sense, and that now has some kind of, in some kind of way, determined the mass distribution of our. You don't hear me? Okay, so when we go back to the Big Bang, then people talk about quantum fluctuations, and then during this area of hyperinflation, these get magnified to let's say, macroscopic effects. And then that's what they use to, let's say, explain the mass distribution in the universe and why it's not homogeneous and so on. So in some sense, you have, let's say, the gravity part of it, how the mass is distributed, how space-time is bent, let's say. But this is then again due to the quantum effects or the quantum fluctuations that during the Big Bang. So there is some. I'm going to say they're coupled in some way, but it's not really a coupling. I guess they're not very separated. I don't know, but it seems that at the point of the Big Bang there is some. One is a consequence of the other. Maybe it's badly worded, but. Yeah.
Okay, Jacques.
So maybe rather than thinking of the Big Bang, I was thinking of something much simpler. If you can make it, I think Penrose refers to it as Schrödinger's lump or Schrödinger's mass. So you make a superposition of an object in this position, which will have its own gravity and curved space-time here, and an object in this position, which will bend space-time here. Then how are you going to describe it? So if you make a superposition of the positions of the masses, maybe you need the superpositions of the space-times. If not, maybe that is, according to Penrose, what will cause the collapse. So it's something that could be looked at. And the other thing is that, as you know, I'm a fan of the path integral version of quantum mechanics, where basically what it computes is transition amplitudes between states A and B by looking at all the possible ways to go from A and B. In quantum field theory, by looking at all the possible realizations of a quantum field, attributing some weight to that, and then summing over it. Right? So now we do that for all the possible configurations of a field on some space-time, but it's always the same stage. So it's all the possible histories of the actors on a stage. But it seems to be, to me at least, nicely symmetrical if we would somehow also make this kind of take into account all possible stages on which these actors could move, and also attribute to them a weight in the sense of the path integral. So that's, but that's, I have no idea how to do that.
Do you see that as a merely calculational tool, or
As a what?
do you see that merely as a calculational tool, these path integrals, or do you think there's some reality to all these paths as well?
No, I would associate, but that's very personal. It's a belief. It's not science. I would associate, yes, a reality to all these different possible possibilities. They have to interfere to create our reality. They have to, be taken into account to do that.
Okay, thank you, Jacques. So about the point of the gravitational collapse, so gravity that could play a role in this collapse, I would like to ask Franck to comment on this, because he has done some work on gravitational collapse, right? So can you maybe weigh in how including gravity could actually help us to interpret quantum mechanics?
Okay, you are referring to a very simple model that was almost a toy model developed for fun. The idea was the following. If you take, as was said, it's very difficult to combine standard quantum mechanics with general relativity. It works very well with special relativity. With general relativity, we have paradoxes, like the one that was mentioned a few seconds ago. When you have the same object that is in superposition of state in different regions of space, it automatically creates a superposition of space-time in general relativity. So the idea was, after all, we have this wonderful DBP theory, and why don't we decide that the source of gravity is these Bromian positions, since they constantly occupy a single point of space. Then gravity could become as, between quotation marks, as classical as the Bromian position. Now, this kind of idea was also first developed by Lajos György in Budapest, I believe. So then the next idea was to say, okay, now we have the gravitation that is created by this Bromian position. Now, can we put on this scheme Penrose's idea of relating collapse and gravity? And the model proposes to change slightly the Newton gravitational constant by adding to it a very small imaginary component. Totally artificial, I agree. And surprisingly, it works very well. It gives results which are very critical. It gives the dynamics of the collapse that sounds plausible. Now, it's not relativistic. It's very artificial in a sense. So it's a model, but it's more for fun than a serious theory.
Okay, thank you. So we have some more fun questions that we also collected through the questionnaire that you filled in, that were about basically how far can we push quantum mechanics, how macroscopic can we get this. Macroscopic, not microscopic, to be clear. So maybe a question to open this topic would be, can we make, in principle, or maybe in real life, arbitrarily large superpositions? No, I think it's not something to vote. I mean, you can vote if you like. Yeah, you can vote. Yeah, let's vote. So blue means you can make arbitrarily large superpositions, and red means you cannot. Let's vote.
So the question is whether or not we believe in Everett's theory.
No, the question is if in principle, arbitrarily large superpositions exist.
Which is the case in Raedt's theory.
For instance, yes. Oh, okay. I see Hans saw too many blue cards, so he switched to red. So let's hear Hans again.
Yeah, so I only have a problem with the word exist. So you can have phenomena, macroscopic phenomena that show wave mechanical behavior. There is no problem with that. Or even wave mechanical behavior that would be typically quantum mechanical. But that doesn't mean the superposition exists. The superposition, again, is just, I think, Dirk already mentioned that, it's just an expansion in terms of basis states. So, I mean, it's a mathematical tool to do certain things, you know? There is only one wave function. If we stick to quantum mechanics, there is one wave function, and we can write it as a sum of many other basis states, if you like, and interpret this as a superposition. Do they exist? Yeah, they exist in our mind. You
know? Pieter?
No, I was wondering if it wouldn't be more interesting to rephrase the question and ask, on what level could quantum mechanics still play a really important fundamental role? I mean, clearly, physics needs quantum mechanics. We saw chemistry mentioned as one beautiful application of quantum mechanics. If you want to understand molecular behavior and chemical reactions, you will need quantum chemical calculations. But what about biology? Does quantum mechanics have to play any really important role in biological systems? Can they somehow make use of some of these typically quantum effects? And we could, of course, go up, all the way to consciousness and ask the same question. Is consciousness somehow something that needs to rely on quantum mechanical effects to be able to exist? I think that would be a much more interesting question, because we see that there have been developments that are now called quantum biology, in which even such a macroscopic and complex wet environment still seems to be able to tap into these quantum mechanical superpositions and effects to, for example, follow the magnetic field of the Earth and other applications.
Okay, that's a very good point. I also wanted to go there. So, yeah, let's take the vote. Can quantum mechanics lead to the emergence of something like consciousness? Right? So if you say that it can lead to the emergence of consciousness, you can say blue, and otherwise you can say red. The question is, can quantum theory lead to the emergence of consciousness? Maybe Jacques, you can comment, since you were kind of holding up the blue one.
It's what you mean by emergence. I mean, it was believed before that maybe even classical mechanics can lead to the emergence of consciousness. So maybe the question is, do we need something more than classical mechanics to explain human behavior? Or consciousness.
Do we?
And then you can even ask, do we need something more than quantum mechanics to explain human behavior and consciousness, right? So those are...
Dirk?
Long time ago, I did work on neural networks, artificial intelligence. People are not even sure what consciousness is. Okay, so I cannot discuss whether consciousness will play a role, because I don't even know the definition of consciousness.
Okay, thank you. So I think now we'll put actually the questions that you've been submitting on the screen, because we haven't forgotten about you. And so let's just ask some of them to the speakers. So.
Maybe instead of scrolling, I still kind of remember it. It was a question about the very first topic that we actually discussed. So it was, I think, related to what Hans presented. When you use, like, let's say, computers to simulate physics, the computers, of course, are using pseudo-random number generators. But quantum mechanics is then supposed to be like truly random. So does that have some? Does that introduce some fundamental shortcomings in these simulations? Can you pass the microphone?
Yeah, I would say again, this is always the same problem. Why do we even come to the statement that quantum mechanics is intrinsically random? There is no evidence for that. How could there be? If you do an experiment and there is data, the data is finite. And by definition, that cannot be random in the mathematically strict sense. So you cannot even decide whether it's truly random in a mathematical sense. So I think this statement that quantum mechanics is intrinsically random is just nonsense. It's really nonsense. I mean, it fits into a certain belief, I know that. But you cannot verify or disprove. So what are we talking about? So when we use a classical computer to generate random events, it is sufficient that these random events are random to everybody looking at them. If you cannot decide or not, say, figure out what a pattern is, then it's random to you. No, it's okay.
Okay, yeah, maybe we can continue with another...
Then it's random to you. No. And that is sufficient.
Okay, thank you. So maybe a question here. How can we have interference without waves, as has been implied by the gentleman on the far right with the elephants? I take that this is not about political opinion. So maybe someone can answer this. How can we have interference without waves? Can we?
Should I answer that? I think so, right?
You can, yeah.
Well, say if we take the people here in the room and we give them instructions to leave the room, certain type of instructions to leave the room by one of these two doors, and then behind the doors collect them. Well, we don't have enough people to have nice interference patterns, but we can show interference with them. It's just about the rules. You just have to specify what each door is doing to the people that is going through them to produce an interference pattern. And this you can show by a very simple computer program. Actually, from my website, you can download one typical, say, realization of it, written in JavaScript, very easy to see. And I challenge everybody to find a signal of a wave in that program. There is no wave, there are only individual objects making movements, going through these slits, and producing the interference pattern as it was observed by Young many years ago. So it's really no issue. It's very, very simple. You only have to think out of the box. That's it.
Okay. So there's another question I like, which is, does any of the panel feel very strongly that at least one common interpretation is truly false or incorrect? That's maybe nice to me.
Well, so because you say, is one interpretation truly incorrect? Well, I think the many worlds theory, it's an interesting idea, but it hasn't been fully worked out yet. Because in the many worlds theory, where do probabilities come from? In the many worlds theory, everything happens. So like in standard quantum mechanics, where do probabilities come from? There's the collapse, which happens with a certain probability. So that's where you get your probabilities from. In the Bohmian theory, where do you get your probabilities from? Well, the initial position might be different from one run of the experiment to another. That's where your probabilities come from. In the many worlds theory, you just have the wave function. Every outcome of a measurement is realized in some world. So why is one world in a certain sense more likely than another? No, they just all happen. Okay, so they all have probability 1 to be realized. So where does the usual quantum statistics given by the Born rule come from in the many worlds theory? So people have tried to answer that answer, but I haven't seen a satisfactory answer.
I think the proof of the pudding is always in eating, and for me eating is the experiment. Even in many worlds interpretation, can you design an experiment where you can link into different worlds? Because if you can never do that, then it's an irrelevant question. A question where you can prove there's never an answer, not America doesn't exist because we are not there. No, proven you cannot. For instance, relativity theory, every speed is smaller than the speed of light. There is, let's say, a mirror theory where every speed is larger than the speed of light, but they can never communicate. So whatever you say about both, you can never prove. And if you can't prove, it's an irrelevant question.
Yeah. Well, I'm even saying something more, that even the double slit experiment, the statistics for the double slit experiment, how do you account for that in the many worlds theory? It's unclear to me.
Well, and I think the obvious one would be Copenhagen. I think Copenhagen is clearly false, or at least, it's not precise enough, using very, vague and woolly terminology. And I would be tempted, because we mentioned it already, venture to say that the GRW interpretation hasn't been falsified yet, but I think it's likely to be falsified in the near future.
Maybe a follow-up question on what Dirk mentioned. So you talk about experimentally verifying these theories, but then what I remember, what Hans said, is that whatever experiment you do, it's always, let's say, a subset of the data. So what even is the point of the, or do I misinterpret it? So with regards to the Bell test, you mentioned that you always are doing your analysis on a subset of the data, so it's not the full data that's available in the universe. So in essence, your experiments are essentially flawed, it seems.
No. You have to be a little bit careful. My statement about using subsets of data only refers to these Bell tests. If you do the two-slit experiment, you don't have to do that. Or you do other experiments, you don't have to do that. Only if you want to have these particular violations of these inequalities, you have to consider subsets.
Okay. Thanks for the clarification.
Yeah, that brings us to the next question I see here. So you mentioned it can be difficult to work with these violations because this theory is generally accepted. So do the people sitting here believe that it's this day more difficult to be critical in science, as it seems more frowned upon whenever a scientist is critical of general accepted theories? Jacques?
I think it's always been difficult to go against the common sense of science, right? This is always been a challenge, but it's always necessary to challenge what is going on. So that's it's, I would say, not more than before.
If I can say, I think I agree, and there are two examples. Yeah, Alain Aspect, for example, who had this brilliant idea of actually trying to perform the Bell experiments, tells the story beautifully in his latest book that he went to see John Bell himself at CERN to ask him for advice and to tell him about his big project. And the very first question Bell asked Aspect was, well, do you have any kind of permanent position? Because basically, trying to perform those experiments was considered academic suicide in those days. So yeah, of course, I think even back then, being bold and critical and trying to perform such experiments was definitely frowned upon. Another story is Costa de Beauregard, who tried to understand non-locality by invoking retrocausal influences, so where a cause can happen after the effect. So causes can actually travel along the backward light cone. He was a student of Louis de Broglie, who immediately said, I mean, don't publish this because you will never have a future in academia. And it was only when Feynman came along and had this idea that, you know, electrons and positrons are just particles, you know, traveling back and forth in time, and had these same kind of very wild ideas, that Louis de Broglie gave his green light to Costa de Beauregard to publish his papers. So I think we see throughout the whole of history that, yeah, of course, you will be frowned upon if you come with a very new and daring theory, but that's what is needed if we want to make any progress in science.
Dirk?
Maybe not relevant, but it's even more dangerous to be critical on climate change.
Okay, a very good point. I cannot disagree with. So maybe we will take for 10 more minutes some questions from the audience, straight from the audience. So, okay, I will go with the mic.
Thanks a lot for the interesting discussion. I have a question, and always it will make me crazy. So we assume that quantum mechanics is non-local, but we cannot use these properties to transfer information faster than the speed of light. Why this is the case?
Maybe I can shortly answer that. So it's indeed that's a natural question to have, right? Like the short answer is like in theories like standard quantum mechanics or Bohmian mechanics, is that this non-locality is washed out by the statistics. Okay, so there's non-local influences. So if I have this singlet state, which you might know, I don't know your background, but so that says that like if I measure this particle spin up, then the other one will be necessarily spin down, or vice versa. So there is an effect. Measuring this one up will cause the other one to go down. Can you use that to signal? No, because the guy on the left here, or the woman on the left here, what's the chance of seeing up or down? Well, it's 50%. Okay? So whatever the guy on the right, so that's even a theorem, whatever the guy on the right is doing, it's not going to influence the statistics over here. Even though for each individual system there's a non-local influence, that non-local influence is washed out by the usual statistics given by the Born rule.
But after measurement, you remove the randomness of other unmeasured one. So when you measure one entangled one, then you already destroyed the randomness of unmeasured state. So that there is determinism over there already now.
Yeah, indeed. So, like, before you do the measurement, there's no definite state of spin here.
Yeah.
But doing the measurement over here causes that party to take a definite state. And that's the non-local effect, very clearly in quantum mechanics. Okay?
Sorry, but I mean, you should really look at how the experiment is done. So when they do the experiment, they have a source that is emitting pairs of light. They go through fibers, they are detected, and they are recorded on a hard disk, the outcomes. And then after all the events have been recorded, whatever they are being analyzed. That is how the experiment is done. So you cannot say that one photon flips, the polarization of one photon flips, and then the other flips too. This is total bullshit. No? So the only thing you can say is there is a certain correlation. You calculate the correlation based on the data. which is a valid thing to do. And on the basis of the correlation, you make a picture. And this picture, in this case, if you do the coincidences properly, matches partially quantum mechanics and actual data. I can give you the data if you like them. Actual data violates quantum mechanics. So, of course, that is never said in the literature, but I can give you a reference to one of our papers where we really show that, using existing data. So the situation is not, it's like you have a picture, a theoretical picture, and then you argue that this theoretical picture is also realized in the laboratory. It's absolutely very, very different. The laboratory experiment is very complicated, and there are many aspects which are not talked about when they publish these results. And they all play a role. So it's not that simple to argue from the theory to the real life. You have to argue from the data that you have and then try to make conclusions. That's the way to go.
Okay, thank you. Let's take another question.
Wait, we have a short comment from Pieter.
No, I just wanted, because Raedt mentioned the Bell telephone, which is impossible, unfortunately. Another beautiful example is quantum teleportation. So there as well, the key, of course, is to use entangled particles, which can influence each other non-locally. And yet, if you look at the quantum teleportation protocol, in the end, you still need to send 2 classical bits via, classical means, via light signal, of course, and that is limited to the speed of light. So there as well, even though it is possible to teleport particles from one place to the other, that is limited to the speed of light. So if you would like to teleport a particle to another galaxy light years away, even though you fundamentally make use of those non-local influences, it will still take light years to actually terminate the teleportation protocol, because you still need to send those classical bits of information. So it's interesting that somehow we have these non-local influences, we use them, we're sure that they are there, and yet we're always limited to the speed of light whenever we try to use it in any kind of technology.
Okay. So when 2 particles are entangled, can we think that they are creating a wormhole so that you observe non-local phenomenon? Can you? No? So when 2 particles are entangled, that you are observing non-local phenomenon, because when they are entangled, they are creating wormhole. And when you measure that, one wormhole breaks down. That's why you observe non-local phenomenon.
Okay, yeah. So maybe let's just repeat what I heard, right? So the thing is, like, if you have an entangled state, some non-locality must go on. You say, maybe the structure of space-time is different. If the 2 particles of the entangled system, you might think of them as far away, but in reality, there might be some wormhole in space so that they're really close by through this wormhole. Yeah, so that's an idea that has been floating around since really a long time, okay? But I'm not sure anybody could make sense of that.
I think it might be a better idea to have this discussion at the reception.
Yeah,
so maybe one more question from the audience.
Yeah, maybe one more question and then move to the reception.
Thank you. I had one question about the many worlds interpretation. I've heard it mentioned today, and I've heard it before as well, that one of its flaws, or maybe its main flaw, is that it doesn't lead to predictions for expectation values because it assigns equal probability to each possible universe. So I think I'm just missing something, but to me this sounds very similar to classical thermodynamics, where also each microscopic realization is equally probable, and the probability of observing something macroscopically is just given by the number of configurations that leads to this macroscopic outcome. So I think I'm just very naive and missing something, but I would appreciate if someone could explain why I could not just conceptually infer expectation values just by the number of universes in which spin up or spin down is realized. Yeah, thank you.
Even in thermodynamics, right, the actual state of the system in the world. Like for example, the gas molecules here in this room we can describe thermodynamically. Okay? But of course there's, according to classical mechanics, there's a very definite state of all these particles here in the room. Okay? I said according to classical mechanics, right? So if classical mechanics is right and we think it describes the gas molecules as we usually think it does, well, according to that theory then...
Can I add something to locality?
Yeah, short.
Because people discuss about, entangled states, two particles. But even in electromicroscopy, if you try to do a double slit experiment, when Neumann paradox says that whenever an electron is detected along one of the, it cannot be detected along the other one. This is a kind of interaction. Now, if the coherence length is large enough, you can make this distance between the slits infinitely large. So then this knowledge, this interaction of when the electron is detected here, it cannot be detected there and vice versa, should be very fast, faster than you say speed of light. But speed of light is a classical concept, You cannot, what I've seen in my world, many people make mistakes by using classical intuition at the quantum stage. You do totally wrong. These are waves and you can only interpret after the detection, you see. So in this case also saying speed of light, no, it is immediate because,
Okay, thank you for this comment. We will soon go to the reception you've all been waiting for. But first, I would like to offer our speakers a chance to give you one final message that they maybe should take away from this evening. So maybe in one or two sentences, we can go over the speaker and they can shoot something towards the audience. So maybe we start with you, Hans.
But keep the sentences fairly short because they can be formulated long.
Yes, so I would say don't reason from the theory to the data, but do it in the other way around. Start from the data and try to fit or find a theory that explains the data.
Thank you. Jacques?
So maybe I would respond in one sentence that the theory of quantum mechanics that we have is the most successful at explaining the data that we have, not just of the experiments that we saw here, like double slit or Bell, but also very complex things like these particles that get collided in CERN, or very small shifts in spectra of atoms. So it's very hard to beat that.
Thank you, Jacques. Frank?
I'm a physicist, so my hope is that a clarification on the quantum theory will come from the experiments. Until now, no experiments has been able to violate quantum mechanics, but I do hope that one day we will find something wrong in quantum mechanics, and then we might understand it better.
Thank you. Dirk?
I think our goal is to match with experiments. We try to improve the experiments. There is a limit. At the moment you have a theory that explains all experiments, then you don't need any more philosophy or discussions.
Thank you. Bart?
Yeah, experiments are of course very nice, but it's also interesting to think. So I think there's two main open problems with theoretical physics. One is how to combine gravity with quantum systems. Is gravity classical? Is it quantum? Nobody knows. There's a lot of options on the table. And the other one is the measurement problem. Okay? So one can push that, and it should be pushed on the experimental side, but it's also worth thinking, maybe on the theory side, is there some interesting ideas we can develop? Maybe even these two problems might be combined, and thinking about quantum gravity, how quantum gravity should work, can also involve ideas coming from quantum foundations.
Thank you. Pieter?
Yeah, well, I would add that we all agree that quantum mechanics is a hugely successful scientific theory, but without an interpretation, any scientific theory is just a piece of mathematics. And so we do need an interpretation, whatever will turn out to be the right interpretation. We do need an interpretation in order to know what quantum mechanics tells us about the world, what the ontology is like according to quantum mechanics. And I think that is hugely interesting, important, and fundamental question that should be tackled by physicists, philosophers, and other scientists.
Okay, thank you. So let's thank our speakers again for the interesting discussion. And now let's continue the discussion with a little drink and a little snack outside of the lecture hall. Sorry, speakers, before you run away, we still have some gifts for you.